Hello everyone, I'm really excited to be here. This is my first time at Try Swift and I'm really enjoying it. Today I would like to share my perspective on the evolution of SwiftUI as someone who has been using it since its very first release and also contributed to its development at Apple. Let me introduce myself first. I'm Natalia, an iOS developer based in New Zealand. I work in my own company called Nil Coalescing. I have a technical blog where I share articles and tips for building apps for Apple platforms. And I also write books for Swift and SwiftUI developers. Before founding Nil Coalescing back in 2022, I was part of the SwiftUI team at Apple. I was in charge of the text and model presentation APIs, and I contributed to other parts of the framework too. In this talk, I would like to give you a deeper insight on how SwiftUI develops and evolves. We'll cover the main drivers of change in SwiftUI. I'll also share a little bit about the process that happens before a new API can be added to the framework. Then, we will examine 3 major changes in SwiftUI up close. And finally, we will talk about why it's important for us, developers using SwiftUI, to stay up to date with the features. Let's start by looking at what drives change in SwiftUI. SwiftUI was introduced in 2019, and its first version was very limited. It was basically impossible to build a full app entirely in SwiftUI. But this has been changing over the years. The second release of SwiftUI added the SwiftUI app lifecycle, new layout primitives, and more built-in native controls. The subsequent releases introduced searchable and background materials, partial sheets, and a native way to share content. And we continued getting new features year after year. As we can see, many changes are driven by the goal of making SwiftUI as feature-complete as possible. But SwiftUI is also part of the wider Apple ecosystem. It has to evolve together with the platforms it runs on. For example, when iOS introduced widgets on the home screen, SwiftUI gained new APIs to let developers create and customize them. And we also got new APIs that were motivated by widgets, but can be used in other contexts too. Then, a few years later, a completely new platform arrived. SwiftUI had to expand so developers could build Vision OS apps. Several specialized APIs were introduced to handle new concepts like volumetric windows and immersive spaces. SwiftUI also matures alongside the Swift language itself. For example, when Swift concurrency was introduced, SwiftUI gained the task modifier and the async image API. The SwiftUI team also listens to developer feedback and tries to address reported problems and limitations. The main tool for gathering this is the Feedback Assistant app. Issues submitted through Feedback Assistant are reviewed and processed first. Then the SwiftUI team decides if they align with the direction of the framework. If they do, they may be addressed in upcoming releases. The more requests there are for similar things, the more likely they are to be prioritized. I know that submitting feedback can feel like it goes nowhere, and some submissions may never be addressed. But it's still important to continue doing it. I have personally fixed many bugs submitted through Feedback Assistant while I was on the team. And I also had some of my own submissions addressed later when I was already on the outside. Now that we know what motivates change, we can talk about how API updates come to life. I will share what I can and what I remember from my time on the SwiftUI team. The internal process for SwiftUI evolution is very similar to Swift evolution. Someone on the SwiftUI team has to come up with an API idea first. Then they have to write a SwiftUI evolution proposal. The proposal would include the feature name, the author, and what motivated the idea. It would describe the solution in detail and include the suggested API design. At this point, it would just be the API declaration, not the implementation. The proposal would also include a section listing what alternative solutions the author considered and why they were dismissed. Some proposals conclude with a planned future direction for the API. When the proposal is completed, the review process starts. Anyone who has access to the SwiftUI evolution repository can comment, raise concerns, ask questions. When the proposal gets approved by other members of the SwiftUI team, the author can start working on the API implementation. Sometimes the approval can be achieved quickly, but quite often it will start a complex discussion with many conflicting opinions. Big changes would usually have a working group of a few SwiftUI engineers meeting regularly to plan the APIs. It can take many months from the initial API idea to its implementation and integration into the framework. Creating new SwiftUI APIs is not an easy task. It requires a lot of patience and great communication skills, in addition to technical abilities. But the job is very rewarding. Every SwiftUI engineer has a very big impact on the future of the framework. I think it's easier to understand how SwiftUI evolves in practice and what that means for developers by looking more closely at some big changes that have been implemented. One of the most notable changes was the redesign of the navigation APIs in iOS 16, when navigation view was replaced with navigation stack and navigation split view. Let's examine how and why it happened. Here is how we would create a list with navigation links and state restoration using old navigation APIs. We declare a navigation view with a list, and we wrap every list row into a navigation link with a tag and a selection binding. This type of navigation link was the only tool we had for programmatic navigation. In this example, we are using it for state restoration from scene storage. Let's see how this code worked in practice. First, we tap on a row that is already visible on screen to navigate to its detail view. Then we return to the home screen to trigger SwiftUI to save the scene state. And we restart the app from Xcode. The navigation state gets restored without any problems. Now, we will scroll to the bottom of the list and select a row that was not visible before scrolling. We repeat the steps to check if state restoration is working as expected. We return to the home screen and restart the app from Xcode. We can see that this time the navigation state was not restored. This example demonstrates that the first version of the navigation system in SwiftUI had some problems. Most of the problems were happening because the navigation view did not have a single source of truth for its navigation state. Instead, the navigation state was derived from the state of navigation links inside that view. Our state restoration worked for the first row selection because SwiftUI processed that row on app launch. So it could extract the navigation state and the link and update the UI. The other row that we had to scroll to is not processed on app launch. The list view loads its rows lazily. SwiftUI did not even know that row was supposed to be selected when the app started. That is why state restoration did not work. Developers had to come up with many workarounds and hacks to bend the old navigation system to their needs. And the SwiftUI team was gathering all the feedback and making notes. Those reported issues were the motivation for the full redesign of navigation APIs in iOS 16. The SwiftUI team iterated on the new API design for a long time. The new APIs had to be simple to use, but flexible enough to support many different use cases. In the end, the team agreed on a set of navigation components that included navigation stack, navigation split view, navigation path, new initializers for navigation link, and modifiers for declaring navigation destinations. Both navigation stack and navigation split view allow for the source of truth that driving navigation to be declared at the root. Navigation stack can accept a binding to a navigation path, while navigation split view can contain a list with a selection binding. Here is our previous example updated to use the modern navigation APIs. We replace the navigation view with a navigation split view and pass the selection binding to the list. We're using the navigation split view instead of the navigation stack so that our app looks great on iPad too. Notice that now the navigation destination is declared at the root as well, in the detail part of the navigation split view. This allows SwiftUI to process the destination even if its corresponding row is not visible on screen when the app launches. Let's test our new implementation. We scroll down the list and select one of the rows at the bottom. Then we return to the home screen and relaunch the app from Xcode. The state restoration works as expected. This shows that the new navigation APIs are more reliable and suitable for real-world use cases. Old APIs don't just get replaced for no reason. If an API is deprecated or its usage is discouraged, it's because it's considered potentially harmful, based on developer feedback or other factors. For the framework to improve, sometimes APIs just need to be rethought, like it happened with navigation. But sometimes there needs to be a completely new system in place to enable the creation of better APIs. And this brings us to our next evolution example, the introduction of the observation framework and its integration with SwiftUI. In early releases, SwiftUI was tightly integrated with Combine, and we relied on the observable object protocol for reference type data dependencies. But with the introduction of the observation framework in iOS 17, the usage of observable object started to be discouraged. We could now move to a more modern alternative, the observable macro. Let's see why this move was needed. Here we are using an observable object to store theme settings. It has two published properties, list theme and row theme, so our UI will update when these properties change. Our view with the list of cats stores an instance of this object in a state object property. It reads the list theme property of the object to update the list row background. It also passes this object down to its subviews, cat row and theme settings view. The cat row view reads the row theme property so it can update the foreground style of the cat name text. The theme settings view provides a form for updating both the list theme and the row theme property. Let's run the sample app and see how views react to theme changes. The cat row view depends on the row theme value of the theme settings observable object. Its body will get reevaluated when this property changes. We can confirm it by placing a breakpoint and updating the settings in the simulator. We can see that every visible row gets updated, and this is expected. Now we can try updating the list theme setting. The cat row view does not read that setting. There is no need for its body to be reevaluated. However, we can see that our breakpoint is triggered again for every row. With the observable object protocol, when any of the published properties change, all the views that read at least one will get reevaluated. This may not be a big deal in a small sample project, but it can cause some serious performance issues in real apps. When we had no better alternative, it was recommended to split our observable state into many small objects to minimize view updates. The SwiftUI team was looking for a better solution, and we now have one thanks to the new observation framework. Now, instead of using the observable object protocol from Combine, we can annotate our class with the observable macro from observation. All properties of the observable are tracked by SwiftUI, so we don't need to mark them as published. We also no longer need old property wrappers such as state object and observed object. Instead, we can store observable classes directly in state. If a view needs to create bindings, we can annotate an observable instance passed to that view with the new bindable property wrapper. Here is how this migration can be implemented in practice in our sample project. The cats view that displays the list of cats now stores the instance of our theme settings observable in state. The cat row view receives that instance as a regular stored property. We don't need any annotations here. SwiftUI tracks changes to properties of an observable automatically and updates views that depend on them. The theme settings view needs to create bindings to both list theme and row theme properties to pass them to color pickers. Here, the theme settings instance has to be passed into the view as a bindable. We can run the app again to see how modern observation APIs reduced unnecessary view updates. We can change the list theme as much as we like. The row view bodies will not be reevaluated. With the new observable, SwiftUI only tracks the properties the view reads. Changes to other properties in the class are ignored. That's why it's important to adopt modern observation APIs in our apps to minimize view data dependencies and potentially improve performance. Not all the API changes are motivated by problems in older versions. Sometimes APIs can evolve because additional capabilities become possible. This is what happened with the improvements to rich text display. In iOS 15, the Foundation framework introduced the new attributed string as a modern type-safe alternative to the old NS attributed string. The SwiftUI team and the Foundation team worked closely together to integrate this new type in SwiftUI. And this collaboration opened up new possibilities. We can display rich text in SwiftUI by passing an attributed string directly to a text view initializer. We can also include markdown syntax in a localized string key, and SwiftUI will parse it automatically. I actually implemented these APIs in SwiftUI, so I'm excited to share some details about how they work and how they came to life. Displaying rich text with an attributed string is really straightforward. We just define an attributed string, assign the attributes, and pass the string to text. It's worth noting that SwiftUI will only recognize attributes that are in the SwiftUI attribute scope, such as foreground color and background color, for example. It will also recognize a few attributes from the Foundation scope, like inline presentation intents and links. Developers often ask why there is this limitation. Well, I did my best to implement as many attributes as possible at the time, and I think that support remained limited because it was likely considered lower priority than other focus areas. So if you would like rich text display to be extended, you should definitely consider filing feedback. Now, let's look at the other change that was introduced at the same time. This one is a bit less straightforward. Starting from iOS 15, text view can automatically parse markdown, but only when created with a string literal. When we create a text view from a string literal in SwiftUI, the string is converted into a localized string key automatically, because localized string key conforms to expressible by string literal. This text initializer looks for a matching translation in the bundle, and if there is none, it defaults to displaying the original key. This specific initialization path was extended with markdown parsing. If we create a text view from a string variable, then the string is simply displayed as is. No additional internal logic runs under the hood in that case. When planning this change, multiple variants of the API were discussed and argued about many times. In the end, it was agreed that letting text process markdown automatically was the right way forward. It didn't have a noticeable negative impact on performance and aligned with the SwiftUI approach to other APIs. The framework keeps the call side simple and does the smart thing automatically. But to make sure that this change doesn't accidentally break existing code, an additional check was included. The change only takes effect in apps compiled with Xcode 13 or newer. Markdown parsing is done using the attributed string under the hood, so this capability was directly enabled by the evolution of the Foundation framework. As we have seen, there are many factors that influence the evolution of SwiftUI. New APIs are introduced to improve and refine functionality and to keep up with the evolution of Apple platforms. There is always a good reason behind the change. Some new APIs can improve performance or reduce the number of bugs. Others can bring new capabilities and improve user experience. To be aware of the upcoming changes, we should test our projects with beta Xcode and beta OS versions. We should also carefully review all the release notes of SwiftUI. They usually explain what changed and why. Sometimes they even mention issues and include recommended workarounds. It's important to address all the deprecations first. If the SwiftUI team made a decision to deprecate an API, it means that it's now considered potentially harmful. It may introduce subtle bugs or performance issues. Or it may not be compatible with newer OS versions. If an API is deprecated, it will no longer be updated or improved, so it's best to stop using it as soon as possible. In large projects, it can be difficult to adopt all the required changes at once. It's important to plan for changes and make them incrementally. We should have a roadmap for how we get there eventually. Embracing evolution is always a good thing. We can benefit from the latest and most improved version of the framework. By staying current, we can make our development process more efficient and keep our code base ready for whatever comes next. You can find the summary of my talk and links to some extra resources from the link shown on screen. It also includes my social media handles and a special discount code for my Swift and SwiftUI books. Thank you.